Good afternoon, everybody. So today I want to cross a couple of T's and dot some I's, and maybe even dot some T's and cross some I's to be super careful. We have covered a lot of ground, and I want to give you a couple of examples of cases where you might not be immediately aware where you could use the Poynting vector to get meaningful answers, or whether you might not even be aware that it's a useful concept. First of that is just a resistive wire that carries a current, and you'll find that you'll need the Poynting vector to balance the heat developed and the resistive losses. Another place where you might not expect it necessarily is in the charging of a capacitor. So I want to go over those and just a little bit of the setup. I'm not going to do the entire problem, but you'll have some idea of what other useful situations you might encounter when you have electric and magnetic fields, which is what Poynting's theorem talks about. And then the Maxwell Stress Tensor, appropriately named Stress Tensor, because it's kind of a messy object, and that's with a lot of simplification, and it might not be immediately obvious why you would want to use the Maxwell stress tensor. So I want you to start thinking about the stress tensor in the following way. So compare this to Gauss's law in integral form. So when you have a some kind of a charged configuration, and you take the surface integral of the flux through a Gaussian surface that spans that entire charge distribution, you can tell exactly what that flux is going to be, even if you don't know exactly what the organizational structure of all those charged objects is. It could be point charges, it could be some kind of a weird structure with cavities, but you know that all Gauss's law cares about is finally the flux is going to be equal to the enclosed charge. And then there's 4 pi's and stuff flying all over the place. But that's the beauty of Gauss's law, that it allows you to say big things with very general applicability without knowing all the details. And in fact, it turns out that they don't really matter. The Maxwell stress tensor plays a similar role. So it describes the forces. So if you want to think about it that way, it describes the forces that are acting on an object that could be either charged or could be carrying a current, and or both, when you place it in some kind of a given electromagnetic field. And that given electromagnetic field could be specified due to some externally applied field. There could be E fields, B fields, it could be antennas, could be whatever you want, or the field could be generated by these objects themselves. All you need to know is you need to have some kind of idea what that field looks like. But you don't actually need to know what the currents are, and you don't need to know what the charges are, because we've already substituted using Maxwell's equations the charge and the current distributions, and then we got the stress tensor, which is described exclusively in terms of the fields. So there are situations where it might not immediately be obvious to you where all the charges sit, but you might be able to say something about the fields, and I'll give you an example like that. And then you can use the Maxwell stress tensor in very much the same way as Gauss's law. You could just take a very cleverly chosen Gaussian surface, and you can tell something about the forces that are acting on charge plates of a very funny capacitor configuration without actually knowing where the charges sit. It's a beautiful thing that we're allowed to do it. It just it's sometimes not immediately obvious what the use of such a mathematical monster is. So I hope that I'll be able to clear that up, and then we'll get started finally on the on electromagnetic waves. So electromagnetic waves, we already talked about the wave equation. In I believe even lecture 1, I think we already derived the wave equation. So we'll go over some of the solutions, some of the general properties of electromagnetic waves, and then of course we'll talk about plane waves, and then we'll talk about polarization. You should have seen most of this stuff before, but we'll throw some advanced, Fourier transform machinery at the problem to be able to say, make general statements about the properties of things that are described by these electromagnetic waves. One thing that you should be aware of is that that we will revisit gauges, and the Coulomb gauge is one that is traditionally used and preferred, but you should realize that when we start doing relativity, Coulomb gauge becomes a little tricky to use because it's not immediately obvious that causality is followed, but it has big computational benefits. Okay, so that's the ground that we will cover today, and then I'm not sure if we'll be able to do the last part of chapter 7, which is the harmonic oscillator description of the electromagnetic field. We might be able to, we might not be able to do. We'll see how we're doing, but then we'll be done with chapter 7. So you have seen I'm a little bit behind with everything, but I did post the homework problem sets, numbers 2 and numbers 3, and I pushed those out until after spring break. I put one on Monday and the other on Wednesday because I don't necessarily want you to have to turn in both at the same time, because then, I'm not that guy. But so I'll give you a little bit more time, but it does mean that we'll probably have to move that first midterm, actually the only midterm, out maybe by 1 or 2 days. I'll be able to tell you more exactly where we are with that. And then I should be able to get to grading and all of that stuff pretty soon. The problems in the book are few and far in between. So I might have actually at some point revert to just making problems myself. That'll also hopefully prepare you better for the kind of stuff that you might see in midterms and finals, because there will be twists on what you have seen during the exercises that you were turning in for homework so far. Let's see. Yeah. Okay. So so let's revisit the path that we took. So we had a when we were talking about the Poynting vector and Poynting's theorem. We started with the total energy stored in some kind of a field, which was 1/8 pi, and then some volume integral of E squared plus B squared. And then I'm following Dr. Garg's notation, and then we used the du dt plus Maxwell's equations to arrive at this expression that is also known as Poynting's theorem, which says that the divergence of the Poynting vector plus the current density dotted with the E field is minus du dt. Of course, with the Poynting vector, let me put that here. So that'll be, I believe it's C over 4 pi E crossed with B. So we took a path, and we went from U by taking our derivative to power, right? Makes a lot of sense, right? Because power is what the what that Poynting vector illustrates. It's the flow of power. And then we went from a derived object, we went from the from that power flow, oops, to momentum density. Oops, what am I writing? Momentum density. That was just by taking the Poynting vector and then dividing that by c squared. And then we took the derivative and plus again Maxwell's equations. So we did it twice. Once when we went from potential energy, and then we got to Poynting's theorem, and then we're doing this again with this derived unit of momentum density, and then we arrived at our stress tensor. So the stress tensor, so Maxwell's stress tensor, and using that we get our force. The ith object is minus, this is that Gaussian integral over the edge of some volume of T I j d to s j, and this is the normal in the j direction. J here is the number that indicates that part of the coordinate system that you're talking about, and the Maxwell stress tensor is that kind of rather ugly expression that I don't want to write down right now. I actually might as well. All right, fine. So this is Tij. Okay, that's 1/4 pi. And it's 1/2 e squared plus b squared. This part is diagonal, delta ij. And then you get your off diagonal corrections here. Beta ij. So let's go through symbolically what we could do with these objects. So let's say a very very straightforward situation. Let's say we have a current carrying wire. So this is a current carrying wire. And it's got A, and it carries a uniform current density. Then if this current is flowing in this direction, then that means it generates a magnetic field in this direction. And now, if this, so far it doesn't really do anything, right? So because we, at least, it'll do something with the stress tensor, but not necessarily with Poynting's theorem yet. So in a, if we have a, so ohmic losses, let me draw that, then we have a current density J, which is sigma times E. And that means that we have our E field that is running in the same direction here. And now we have both the E field and the B field right at the edge here. So at the edge here, at the edge, we will get a contribution from the Poynting vector. Now, it's a little hard to see, but you'll actually find that the Poynting vector is pointing in, because that's how the E cross H work out. And it's going in, and it's exactly equal to the power that's being dissipated by the ohmic losses in the wire. So in this case, the Poynting theorem says says because du dt is 0, right? So quasi-static, so we're not changing anything. That the power dissipated by ohmic losses is balanced by the Poynting vector integrated over the surface of the conductor. And why is that? Well, it gets hot. All right. So that's the thing that Poynting's theorem says something about. Maxwell Stress Tensor also has something to say about this situation, but it's a little harder to work with. But for instance, we could take a little piece of, put a little Gaussian surface here with the right symmetry here, and then the Maxwell Stress Tensor, if we do that correctly, would find that both the E field and the B field will cause a pressure to be exerted on the current carrying wire. Now, it's a little harder to see. So both E and B give pressure on the wire. It's a little harder to see exactly what's happening here because you have in the Maxwell Stress Tensor both the electric field and the magnetic field. But if you want to make life a little easier to see to do this, then what you could do is you could say, well, let's assume that this wire is not dissipating. So then your J is sigma E doesn't work anymore, so you don't have to worry about the electric field anymore. And then you have only the magnetic field. So for instance, if you had a superconducting wire. Okay. A second example where you might see this. So let's see, example number 2. The charging of a capacitor. All right, so let's say we're doing this with ideal parallel plate capacitor. Let's say we're charging this positively and this negatively. That means that there's an electric field. Let me make sure that I'm using my colors consistently. Yeah, so there's going to be an electric field here that builds up. So that's going to be your E of t. And because the electric field is a function of time, there is also an induced magnetic field, and that magnetic field is going to circulate. I don't know off the top of my head which direction it will be. I believe this is what you will find. So you'll get a B of t. So this is due to Ampere Maxwell, basically the displacement current term. All right, now we can ask ourselves, what does Sir Poynting have to say about this? Well, Poynting's theorem says that well, you have this balance of ohmic losses and this inflow of electromagnetic energy through the Poynting vector, and you have a change in the energy density of the system. Now, in the charging of the capacitor, if this capacitor is made of parallel, perfectly conducting wires, we don't have to worry about the ohmic losses. So we only have the this term and this term. So then we will find that at the edge here, the electromagnetic energy is flowing into the space of this this capacitor, and that energy that then gets stored in the field is equal to, so Poynting says, energy flowing into the capacitor gap is equal to 1/2 CV squared, which is the energy that's stored in the capacitor. And then now you know how the energy got there. It got there because we moved the field into that region. An example where the stress tensor is super useful. All right, so let's go again to a capacitor, but it's a bit of a funny capacitor. So we're building it like this, and we make it do something like this. We're connecting both with a circuit, so we have some kind of a battery here. So we know that they're going to be at the same potential. Let's call that potential V. And now the Maxwell stress tensor helps you calculate the force on the conducting plates without knowing the charge distribution. All right, so how does this go a little bit? Well, you don't know the exact charge distribution, but you do know one is going to be positive and the other is going to be negative. So your electric field's going to look like this. We can also assume that it's uniform. So in that case, what we can do is we can do the following. We can take a Gaussian surface that looks like this. Go very close here. And we close it at infinity, so we don't have any edge effects. And now if we work out, because we know what the electric fields are in the regions where the field is uniform, so we know E here, and we know E here, and we know it here. E here. If we assume that this crossover is far away from this edge and we don't have any funky things happening, but even if we have funky things happening at this transition, as long as this thing goes from, let's say, a gap of, let's call this 2D to D, then we can calculate the force on that bottom plate by just working out the stress tensor integral over that Gaussian surface. And then the beauty is we can actually also say the stress tensor evaluated over this Gaussian surface, which is the complement of the first Gaussian surface, it's going to look exactly the opposite as the one for the yellow Gaussian surface, because now the E fields are all pointing in the opposite direction, and the normals are all pointing in the opposite direction. So the force on the top plate is going to be minus the force on the bottom plate. Even though we don't really know what it looks like, this is already saying all things will be well. All right. Electromagnetic waves. So we had in lecture 1, we already had our wave equation for E and B. E. Actually, most people write it like this: minus 1 over c squared, d squared dt squared E equals 0. So that's one way to do it. B identical ddt squared B is 0. Of course, it's a 0 vector. Let's see. We have in the Lorenz gauge, we also have a equation like this for the vector potential. Oops, I need an actual A. I think I did that before. And the same for the scalar potential is 0, but of course this one is not a vector quantity, it's a scalar quantity. Now there's a the Lorenz gauge, of course. Let me write that down. The Lorenz gauge is that your divergence of A is mine over C d phi dt. I might have a minus here or a plus here. I could be wrong. Then there's also the Coulomb gauge, which is the gauge where this is 0. We get, surprisingly, the same equation for the vector potential, but nicely, the Laplacian is 0 in this case. So we don't really, in the Coulomb gauge, we don't really need to worry about the scalar potential. And in that case, because our the non-trivial solution would be a wave, right? So that means that we can just get our electric field from the vector potential by taking E. So we have an E would be 1 over C dA dt, and we don't need the phi anymore if we assume that we don't have to worry about this anymore. And then, of course, B would be the curl of A as per usual. So the Coulomb gauge is a gauge that a lot of people use. There's another reason for that, and that is that this Coulomb gauge is also called the transverse gauge. Oops. All right, and now let me explain to you why they call it a transverse gauge. So remember, if you have a Nabla operator and you take the Fourier transform, so I'm going to take the Fourier transform of this thing, then you get ik, and then you are left with the Fourier transform of your A. And the Fourier transform is a linear operation. So if you have a component in the x direction for A, then also the Fourier transform is going to have a component in the x direction. And therefore, that means that if this is 0, because that's what the gauge choice is, that means that K is perpendicular to A. That's why we call it the transverse gauge. So let's get going on the general properties of the wave equation. So for instance, if we take I'm partial to the wave equation for the electric field. So let's say we have the electric field is 0. Then if we take the Fourier transform, and by this we mean the Fourier transform both in x and t, so x and t, so we mean the double Fourier transform of this thing, then anytime we get a derivative, we pick up some kind of a factor that comes out. Now we have to be a little bit careful here because this sign choice that the book uses here is a little bit I'm not using enough space, is equal to minus I omega, and then it's the Fourier transform of that thing in dots. And if we do the same thing, but now instead of the time derivative, we have a partial of, sorry, nabla of something, then that is equal to ik dotted with the Fourier transform, same thing, dotted. So the thing to pay attention to is the minus sign. Even though, of course, in the end, after this little thing, pay attention to the sign, turns out we're actually squaring everything anyway, so it doesn't really matter. So you take the Fourier transform, you'll pick up a ik vector squared, and then you'll end up with the Fourier transform of E that I'll indicate with a little squiggly on top. Now a minus, and this is where we get our minus I omega squared, 1 over c squared E is 0. And that means that we get a k vector squared is omega squared over c squared, if you work out all your minus signs. So therefore, if k squared, k vector squared is k squared, that means that k is plus or minus, sorry, ck is plus or minus omega. So we haven't really assumed anything about our wave equation. All we've done is we've just taken the Fourier transform, and we worked out that once we've done the Fourier transform in both the time and the spatial domain, then we know that there will be two solutions, one where k is ck is plus omega, and the other where ck is minus omega. Okay, your mission. Using Faraday's law, let me write it out. Faraday's law, show that K is, that B is perpendicular to both K and E. I think most of you understood what to do here. So again, the trick is to take the Fourier transform and then convert all your derivatives to the appropriate quantities. So we get I, K, crossed with the Fourier transform of E is equal to, we get a minus minus, so I omega over C, the Fourier transform of B, and then due to the properties of the cross product, that means that K and E form a plane. K and E form a plane. And B is perpendicular to that plane. So perpendicular to both K and E. Done. All right, now we could do the same thing with Ampere Maxwell, obviously. So Ampere Maxwell for sourceless versions. So we have only the displacement current. So taking the Fourier transform, we again get IK cross with B is equal to minus I omega over C E. So therefore, same thing, E is perpendicular to that plane formed by K and B. So we got two planes, and therefore E, B, and K form the three basis vectors of R3. In other words, they're perpendicular to each other, and we can get anywhere with these three, provided that the wave actually gets there. Okay, so let's keep going. So we made some general statements. We know that our K and E, and B are all perpendicular. So without assuming any kind of particular electromagnetic wave, are there things that we can say about this waves that are described by this very minimal set of conditions? Basically, we said, well, it just needs to satisfy the wave equation, which puts places a condition on omega C and K, but doesn't necessarily say anything about the relation of the E's, the B's, and the K's, other than the fact that they need to be all perpendicular to each other. So we haven't really specified. These could be spherical waves, could be plane waves, could have any kind of weird polarization. So let's see if we could say something else about this thing. Well, what does Mr. Poynting have to say about this? So the Poynting vector, of course, S. So that's C over 4 pi, and it's E crossed with B. Now let's work in the Fourier domain because it's useful. So we have it in the Fourier domain. Then we know what the relations are between the E's and the B's. So there are two ways to go. So for instance, we can say, one, we're going to eliminate our B's in favor of E's. So then we get C over 4 pi, and we have our E. We're going to cross that with our B, but our B, meanwhile, is C over omega, K crossed with E, which we got on the previous slide. And then we use our triple rule. So the triple rule that A crossed with B crossed with C equals da 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 da. Where am I? All right, here we go. It's, I can never remember this. It's A dotted with C, B, and then minus AB, C. Okay, so meanwhile, back here. Okay, so therefore we're getting C squared over 4 pi omega. And now our A crossed with B, so A and C, so A dotted with C. Okay, that's good. That's E squared times K vector. That's not a dot product. That's just K vector. Let me make sure that I remove that dot. Okay, minus. Now this second term is going to be 0 because we're going to have the A dot B, which would be the E dot K, and we just showed that that is 0. So this dotted with E. So that's 0 because they're perpendicular. So we get our C squared E squared K vector over 4 pi omega. And I want to simplify this a little bit. So we know that C and K equal omega. So in other words, we can write this as C times K times E squared. And now this is not K vector, but this is K normal over 4 pi omega. And now omega is equal to CK, so there we go, done. So we get a expression for the Poynting vector that is just pointing in the K direction, doesn't even care about what that number is, and it's just going to have the amplitude that is given by the Fourier amplitude of the E field. So there we go. So the E field tells you exactly what the energy density is. So now let's do that for case number 2. So let's do that for the reverse. So we're back at the original position. Now we're going to take our E and substitute in B. So we'll get, let me see, put in E, where's my expression for B? Ah, yeah. Minus C over omega cross with B. Okay. And we again get a C squared over 4 pi, but now of course we have a minus sign, but that's because we have the opposite version. So again, we need another triple rule. Ooh, don't know what that was. We need another triple rule. The rewritten version of this guy. So that's our A crossed with B, crossed with C. All right, that's A dot C, B minus B C A. Okay, so then that gives us a C squared 4 pi omega. Now our K crossed with B, so that's A dotted with C is going to be 0. That first term is 0. This term is 0 because our A and our C are going to be K and a B, and we know that those are perpendicular. So we only have the second term, which conveniently also carries a minus sign. So we'll have a minus here. And then we'll go B dot C, which is now B squared. And dotted with K vector. And now we see that we have an identical expression to the one we had before. So we have our K vector over 4 pi. And then B squared. So that's pretty cool. So this thing and this thing, they are the same. So the electric field component and the magnetic field component carry the exact same amount of energy. So the electric and magnetic field components carry the same energy. And because they carry the same energy, we can describe this in terms of either the electric field or the B field or both if you want. So you could say S is going to be pointing in the K direction 4 pi. And now B squared, okay, so here we go. So that would be B squared or E squared or E squared plus B squared. If you just, so 3 versions written in one go. This is incidentally one of the beauties of the Gaussian system, is that these two magnetic field components, the E and the B components, have the same magnitude. If you were to do this in the SI system, there would be factors of C flying all over the place. All right, and I inadvertently dropped the factor C here. So let me put that in. So there's a C here. And I only was supposed to take one of the C's out. So, yeah, only one. And then, see, nothing happened. It was always there. So revisionist history. Okay. So now that we know this about the Poynting vector, we actually said quite a lot about it. We can also say what the actual energy density is, but getting a little tired of writing all these squiggles. So let's just work with an actual plane wave. So for instance, if we have a plane wave and we have without loss of generality, I can just say it's some cosine omega t minus kc. So this is a wave traveling, and I need some kind of a prefactor. E naught. Traveling in the in this case the plus z direction, and with x component for the E field. That means that K is pointing in the plus Z direction, and you should be able to find what the B field is using that that triple product. Incidentally, if you want to write this in Fourier components, this version, it would become, oops, it would become, in Fourier notation, would just be x hat E naught, and then there will be a delta, and I believe it's omega prime minus omega, and then a delta k minus k prime. Sorry, that would of course not be like this. It will be delta omega and delta k. And then you could work with this whole thing with all the delta functions, but why would you do that to yourself? Okay, so this is what we call an example of a plane wave, and by plane we mean the phase is constant along or across planes that are perpendicular to k vector. So in that case, we get, the E field does at a certain snapshot in time does something like this, and then the B field does, hang on a second. Yeah, so does something like this. And then that means that the wave is traveling in this direction. So that's E, and this is B. Oops. Okay, and this is at some time. In this case, my question to you is, what is the Maxwell stress tensor? So remember, Tij 1/4 pi delta j minus E I E j minus B I B j. And I'm going to let you work on this a little bit. So the tricky part in this is just reading this expression for the Maxwell stress tensor, because it just looks weird, and that's why we're doing this. So if in this case we have a plane wave, that means that the electric field's pointing in one direction only, and the magnetic field therefore is also pointing in one direction only. And if we make our I and J's coincide with the X, Y, Z coordinate system, then even if, let's say, this E field is not zero, for instance, because X is in that instance is equal to I, that means that J component, if J is not equal to I, will be zero, because E only has an X component, right? And the same thing holds for this. And that's why these two terms disappear for anything that is not on the diagonal. And that's why I said it's diagonal. But what it means, what it does not mean, is that when you're on the diagonal that you can throw those two terms away, because they're important. Okay, so what happens when you look at the diagonal element? So the first one is the XX entry. You just write it out. It's E squared plus B squared minus EX squared. Now in this case, because it's an electromagnetic wave, we know that the E squared and B squared amplitudes are the same. So E squared is equal to B squared, which means that this is going to be 2 times the E squared component, which is in the X direction. So therefore, this term is exactly equal to, this term is exactly equal to EX squared. That's where the half disappears because of those E and B being the same. So therefore, this thing is 0. Okay, TYY, something similar happens, except of course now, because we're looking at the YY component, there's no single instance where this thing shows up. We only have to carry the B component, right? So therefore, we get a BY squared. And again, the E squared and the B squared are the same, but now it makes sense to write it as BY squared, because then it is clear that it is canceling with that BY squared, and therefore it is 0. So looks tricky, but once you see it, you cannot unsee it, hopefully. Okay, so the last one is the Z one, which is just going to be EX squared, because there's no longer that subtraction of the EX squared or the BY squared that could happen, and therefore you just get the EX squared. And of course the half cancels because you get 2 times this. Okay, so what is EX squared? Well, I mean, if you want to be really really very verbose, you could write it out. There's a cosine somewhere. There we go. Yeah. So there's an E naught squared cosine squared omega t minus kz. All right. So what does that mean? Well, remember the Maxwell stress tensor says if you place rho's and j's in my path, oops. In my path, thou shalt feel F minus the integral over some Gaussian volume T I J T2 S J. All right. So let's say you have a wave that is traveling in this direction with some S vector, and therefore also has a TZZ. That means that if you place a surface here with a normal in the Z direction, you shall feel a force. And that, ladies and gentlemen, is the radiation pressure. Okay, so in this case, it is the radiation pressure. So all is well with the world. It's an interesting thing to think about what happens when this thing actually starts radiating the field back. So for instance, if this is a perfect absorber, then the electromagnetic field on the left-hand side of this sheet is completely defined by that blue Poynting vector. But now, if this thing is reflecting, so a reflected S, if this also enters the picture, you need to actually include that in your stress tensor, and therefore your pressure is going to be twice as high, right? Because now you have an incoming and an outgoing, and there's squares everywhere. So there you go. All right.